Welcome to this very first session on the topic of machine learning. In the broader perspective, this field also deals with artificial intelligence, computer vision, and to a large extent we'd be talking about the artificial mechanisms by virtue of which we'll try and imbibe the art of learning different patterns in our machines. Since this is the very first session in this series, what I wish to do in this particular session is to provide an introduction, an exposition, and then I would also like to introduce the very first, the most primitive kind of learning mechanism. And to be able to do that, we are also going to introduce the concept of artificial neural networks. If you think about it, machine learning is an ocean, and in the modern era we have seen tremendous advancement of the technology, and there are so many algorithms, there are so many walks of applications in which we have been making use of machine learning, and that's where I believe it's very important to understand the scope of this particular course. And as far as the scope is concerned, predominantly we'll be talking about three different very interesting parts of machine learning. The first part deals with artificial neural networks. The second part deals with fuzzy logic, fuzzy inferencing, and the fuzzy systems. And the last and the third part deals with genetic algorithms. So this journey will take us from very simple, most basic type of systems to the most complex real life systems. Let's begin that journey with artificial neural networks first. And this typical part is also many times referred in the literature as the soft computing part of machine learning. So let's begin our journey with artificial neural networks. In artificial neural networks, these are the major topics that we'll predominantly be talking about. We'll talk about the basics, the fundamentals, different learning strategies, mechanisms. We'll be talking about what is known to us as pattern association, which is quite different than learning, and it takes us in the realms of memorization. So we'll be talking about all these interesting algorithms. A few of them will be supervised, few of them will be unsupervised. And we'll talk about these algorithms as and now when we'll be exposing them to our viewers. But typically these are the topics that we intend to cover as far as the neural network, artificial neural network part of this course is concerned. We typically know that artificial neural networks, particularly post 60s and 70s, they have started finding applications in different walks of life, and these are the typical ways in which artificial neural networks are applied. And the first is obviously pattern classification. Now what do we mean by that? Once we start developing our systems and designing our applications, it will be very clear to our viewers as to what exactly are we talking about. But these are the three different types or classes of applications: the pattern classification part of it, then the control, time series modeling and the estimation part of it, and also the optimization part of it. And using these three different types and classes of applications, we'll be dealing with many interesting real world problems and real world solutions. We also know that a typical artificial neural network system is a non-linear, non-parametric kind of a system. I repeat, typically we also know that neural networks are non-linear, non-parametric kind of systems, and they typically give us an ability to make the entire system, the entire solution go dynamic. So instead of keeping it absolutely static and rigid, we can make our solution go to being dynamic, and that's precisely where the system should be able to learn. Systems should be able to adapt, because the world around us is highly uncertain. In fact, they say that uncertainty is the only certainty of life, and that's where the systems that we develop, they should be able to adapt, to the changes, and that's where we intend to create dynamic systems. These are once again different actual applications of pattern classification. We could be talking about speech recognition, classification of the radar and the sonar systems, remote sensing, character recognition, biomedical walks with the likes of ECG classification, credit card applications, and something that has become very popular of late is data mining and information retrieval. We could also be talking about different applications under controls and time series and estimation with the likes of robo manipulation, machine controls, forecasting, and inverse modeling of vocal tract, for example. Under optimization, we'll be predominantly talking about TSP, which is a very popular problem, traveling salesman's problem, multiprocess scheduling and task assignments, and few very interesting challenges in the field of very large scale integration, that is VLSI technology. These are again few of the real world applications, and you can actually see these applications actually functioning in all these different fogs. However, we'll introduce these applications slowly and gradually to our viewers. So instead of talking the talk, let's start walking the talk, and that's where we'll look at the first most primitive kind of definition of artificial neural networks, and it is defined as a massively parallel distributed computing system. So from the perspective of algorithms, this definition actually makes sense, but intuitionally, if we really try and understand what artificial neural networks are all about, then probably we'll be able to say that it's a massively connected network of artificial neurons. Now, what is the meaning of artificial neurons? How we can build these networks? We are going to see all of that, but slowly and gradually. These are the books, one written by Simon Hekin, that will be typically making use of in this particular course. We always say that we learn from Mother Nature. We learn from biological systems, and it's fun to actually understand how human brain functions. In fact, if we look at it carefully and if we think about it, then human life is all about taking decisions. And the moment I say I am trying to imbibe that and create artificial system, then that system also should be able to take interesting decisions. From the moment human beings get up to the moment they go to the bed, they end up taking so many interesting decisions, either consciously, subconsciously. And human life is all about that. It could be a very simple decision, for example, if I want to drink tea or not, or it could be a very complex decision, whether I want to get married to a specific person or not. Starting from very simple decisions to very complex decisions, human life is all about taking decisions. And that's precisely what we want to imbibe. We want to take this ability of human beings of taking interesting decisions and put that in our machines. However, in order to be able to take interesting decisions, it's very important to be able to understand the systems, to be able to draw certain conclusions, and to be able to learn from the underlying patterns. So we shall make use of these very interesting nitty-gritties of human brain, the so-called biological neural network or biological system, and we will take clues from biological neural systems to be able to then build artificial neural networks. Now, this course is definitely not for those with a very strong background in biology. And being engineers, what we typically do is we restrict our understanding of biological systems only to an extent so that we'll be able to create technology out of it. And that's where, if you look at this particular biological system, you will realize that there is a soma, which is the actual cell, and then there are dendrites, which are sensors, there is semantic gap, and there is axon. So that will be able to connect us one somal cell to another. And let's take clue from all of this, and this will help us create the artificial mechanism. And using this, you will be able to realize that one particular neuron is one particular soma or a cell, and it is made up of what? It is made up of inputs, which are the sensed inputs, and the sensors are responsible for sensing data, and these inputs are then given to one single neuron, one single cell, and the information is typically passed on to another cell, or a final decision is taken. The most important part is all these inputs, they are not neutral inputs. So with every single input there is a weight associated, and the weight could be either positive or a negative kind of a weight. What is the impact of that? We'll see that in a minute. But taking the clues from the biological system, the simplest and the most primitive kind of structure of artificial neuron was proposed by McCulloch and Pitts, and we are going to see that first. However, we must also understand that ANN has certain limitations, and there is a scope which is well defined. That's why we must also understand the assumptions associated with artificial neural network. See, as far as the processing of the information is concerned, the individual cells, the local cells, are responsible for doing that, and they are typically called as neurons. The signal is typically passed between two neurons over the connection links, and that's where they will be able to form a network, and each connection link has a weight associated with it, like I mentioned. And in fact, machine learning is all about deciding upon those values of the weights, and we are going to see that through few examples. And each neuron applies an activation function. Now, what is the role of activation function? We are going to understand that as well. But it is this activation function which is responsible for taking that decision that I was talking about. If the decision is yes or a +1, then we typically say, oh, the neuron was fired. And if the decision is no, or a negative kind of a decision, or a 0 kind of a decision, we typically say that the neuron did not fire. As simple as that. There are certain characteristics which are associated with artificial neural networks. The most interesting is the architecture, the training algorithm. What is the algorithm using which we train our systems? And then the choice of activation function, which activation function we typically make use of, because that's the one which is responsible for taking the final decision. This was the very first, the most primitive kind of model that was proposed by two scientists, McCulloch and Pitts. The most simplistic kind of neuron model, but a very interesting model. And even today, when we build very complex systems, we still make use of this particular model. And if you look at it carefully, this model is a very simplistic model in the truest possible sense. So what we have in this model is an adder, which is typically responsible for adding up all different inputs, and these inputs are represented by y of 1 going all the way through y of z till y of n. And then there are weights associated with every single input, starting with w of I of 1 through w of I of z going all the way till w of I of n. There is a very interesting concept of bias, and that is theta of I, and this adder produces an output which is represented by mu of I, and then this input activates the activation function, and activation function produces the final output which is A of I, and that output is a decision. A very simple, very primitive kind of a model, but a very effective way of representing an artificial neuron. How to build networks out of this, how to build problems, and how to create solutions for these problems, we are going to address all of that in this particular course. A typical neuron model, if you carefully look at the underlying maths, then you will realize that for a 2-input system, it will typically have an equation of a straight line. If it's more than 2 inputs, then the system will typically end up producing an equation of a hyperplane. However, please remember that this system is going to be a simple linear kind of a system. How do we deal with nonlinear problems then? Well, we may convert nonlinear problems into linear problems by virtue of doing some tricks that also we are going to study in this particular course. If the problems are not in the realms of being able to get converted into a linear kind of a classification space, then the underlying maths essentially becomes more complex, and we'll have to solve a very interesting criterion called as Lyapunov's instability criterion. We are going to study one very specific type of neural networks wherein we are going to deal with this. But till that point, all the models that we'll build to begin with are going to be simple linear kind of models, and they will be governed by underlying linear mathematical formula as shown on this particular slide. There are different forms of nets. However, like I said, instead of talking the talk, we will walk it as and how we are going to introduce different concepts and different algorithms. But at this point in time, the viewers can only keep in mind that ultimately neural networks are built in order to be able to solve non-linear and non-parametric systems. So although we are going to start our journey with few very simple linear systems, that is just to elevate our understanding, but the main aim of making use of neural networks is to be able to build the systems which are going to be non-linear and non-parametric in their nature. The different types of activation functions. There are different characteristics that my activation function should typically have. For example, it should have a monotonically non-increasing and non-decreasing kind of a nature. I repeat, my activation function should typically have monotonically non-decreasing kind of nature. The first order derivative and the second order derivative of my activation function should typically exist. And why? That is the question. We are going to study backpropagation, and that's where we are going to understand this in depth as to why my activation function should be able to produce the first and the second order derivative. But these are the typical characteristics that my activation function should typically have. And then the most primitive kind of activation function again could be a linear activation function, which is shown in the graph, and the formula is f of x is equal to ax plus b. It's a simple activation function wherein the curve goes through 0 and it has a slope of 1. It's a simple line, as simple as that. Radial basis function is a very complex kind of an activation function, and we are going to study radial basis function neural networks, and at that time probably we'll expose our viewers to the concept of radial basis. But to begin with, we are going to make use of these two activation functions a lot. The first one, as can be seen on this slide, is a threshold kind of an activation function, wherein we define a threshold, and when the input is more than or equal to this threshold, the output produced is +1. When the input is less than this threshold value, the output produced is -1. As simple as that. The second type of activation function is what is known to us as sigmoidal activation function, and again, when we are going to talk more about backpropagation systems, at that time we'll talk more about the sigmoidal activation function. But to begin with, we'll typically make use of the threshold activation function. Hyperbolic tangent activation function. So this is an elevation on top of the sigmoidal activation function. So let me go one slide back, and if you see the sigmoidal activation function, you will realize the output produced, it ranges from 0 to 1, and that is really good if I am trying to build a binary kind of a system. But the moment I want to build a bipolar kind of a system, where my decision could be a +1 or a 0 or a -1, then my activation function should be able to toggle between this range from -1 to +1, and that's precisely where the hyperbolic tangent function actually gives us that freedom, flexibility, and it toggles from -1 to +1. There are different ANN configurations. For example, a unidirectional, wherein the communication links will typically take us from input to output. My graph could be a fully connected graph, wherein every input is connected with every possible output. I can also have a typical feed forward kind of a network, and this particular configuration is arguably the most popular of all the configurations of artificial neural networks. I can probably also have a network with a feedback mechanism, wherein I want to reduce the system, and unless and until I have a feedback, how can I reduce my error? So it's really good to have that feedback mechanism in place, and by virtue of that I'll be able to create feedback dynamic systems. Now all these systems will be introduced slowly and gradually. We are going to start with simple systems, and then by virtue of understanding the limitations of the previous systems, we'll be moving for the next system in the ladder, and we are slowly and gradually going to introduce these interesting concepts to our viewers. So let's begin. Enough of talking the talk. Now let's, like I said, start walking the talk. And what we intend to do to begin with is once again revisit the McCulloch-Pitts model. So we are going to follow this particular model for quite some time, at least for next 4 to 5 sessions at least. And this is the nomenclature we are going to stick to. So all the inputs to our neuron will be called as x of I, x of 1 through x of z going all the way till x of n. All the weights will be called as w of I of 1 going through w of I of z, reaching out all the way till w of I of n. The bias values will be called as b of I, and the adder is going to essentially add all the weighted inputs into the bias value to produce an output y of in. The output produced by my adder y of in, it goes in as an input to my activation function, and my activation function essentially produces the output of my artificial neuron, and we'll keep calling that output as y. So we'll follow this nomenclature, this terminology all throughout this course. So all the inputs x of I, all the weights w of I of z, all the bias values b of I, the intermediate output y of in, and the final output produced by my neuron y. So keeping this in our mind, now let's start building very simple good looking systems. But before that, just a gentle reminder, we have been talking about this fact that we try and learn from Mother Nature, and one of the brilliant creations of Mother Nature or God is human beings. So we really try and understand how our brain functions, and what we have inside our brain is biological neural network. So we take clues from biological neural network to essentially build the artificial neural network. And if you think about it, this model may look very simple, very primitive, but this is very effective. In fact, this is what we do as human beings. Take an example of smartphones, mobile phones that we have with us, and consider that I want to mimic my system of mobile device using this simple model. It's very much possible. So you'll have your mobile phone right at the center, and we typically receive thousands of calls in a day's time. So all these received calls will be inputs to my neuron x of I, and with every single call there is a weight associated. For example, if I get a call from a good friend of mine, the weight associated will be a big plus value. Vis-a-vis, if I get a call from my boss, for example, and if I'm not in good terms with my boss, then a weight associated could be a big minus value, and that typically gets added up, and it may result into not crossing the threshold value, and my neuron may not fire. So a friend of mine calling me a big positive weight, it will make my neuron cross the threshold value, and the output could be yes kind of an output, a +1 kind of an output. As against that, if I get a call from a person with whom I don't want to speak with, the weight associated is a big minus, that typically gets added up, and it may not cross my threshold value, and the resultant decision taken could be a 0. So you can imagine y as the final output, which could be binary in its nature. And let's start with that. Let's start with building a simple binary kind of a system wherein the decision is very straightforward, a yes or no kind of a decision. And we realize that not every time we'll be able to take a very simple yes or no kind of a decision, and at times there are decisions which are of the nature of maybe or maybe not, or a value could lie somewhere in between yes and no, and that's precisely will enter into the realms of fuzzy systems. But we'll do that systematically, slowly and gradually. For the time being, what we intend to do is introduce you to this McCulloch-Pitts model. It's the most simplistic, most primitive kind of a model, and we'll see if I can build few very simple systems using this model. And once we are confident, once we are conversant with all these simple systems, then we will start building on top of that, and we'll start complicating the matters. So let's start with very simple system to begin with, and let us say I want to mimic certain digital functions, and let's begin with an example of a 2-input AND gate. And you might wonder why at all we are doing this. You might have heard of the concept of universal gates with the likes of NAND gate and NOR gate. So if I can mimic these gates using my artificial neuron, then I should be able to build any digital logic. It could be a logic of a traffic signal, it could be a logic of a lift, it could be a logic of my washing machine, for example, and give me any real life system, and then I should be able to mimic that using my artificial neurons. And that's why there is fun, first of all, building the fundamental blocks. And let's begin our journey by virtue of making use of what is known to us as a 2-input AND gates. So what we are going to start our journey with is this. It is going to be a very simple a 2-input AND function, and we'll try and mimic this 2-input AND function. Since this course is about machine learning, it's all about learning, and I'm also slowly and gradually trying to learn with this stylus system. So my handwriting will be poor to begin with, but it will improve as the time progresses. So please bear with me for some initial time. But we typically know how the truth table of a 2-input AND system typically looks. The system has 2 inputs, and let's name these inputs as x1 and x2. Now we have already decided that we are going to follow this nomenclature. So all the inputs will be called as x of I, and the outputs will be called as y. So it's a simple 2-input single output system where y is output and x1 and x2 are the inputs. And since this is AND gate, we know that output will be high only when x1 and x2, both of them are high. So when x1 is 1 and x2 is also 1, then output y is 1. Typically for all other cases, when x1 is 1, x2 is low, output will be low, and likewise we'll have the rest of the cases. It's very easy to actually see this, and so this is the truth table that we typically have with a simple 2-input AND kind of a function. Now the challenge that lies in front of me is, can I mimic this system using the McCulloch-Pitts model that we have seen. And let me draw this model once again so that it will be very convenient for the viewers to really understand what exactly are we trying to build over here. So this is an example of an artificial neuron in its most primitive form, wherein it has got two components. This is what is known to us as an adder, and then we have an activation function which is responsible for taking the final decision. And we'll be keeping this activation function as a simple threshold kind of an activation function, and we'll call that threshold value as theta value. So what theta value we are going to select, that is something which is part of the design. This activation function is going to produce an output that we are going to call as y. This intermediate output will be called as y of n, and there are two inputs to this system. The first one is x1 and the second one is x2, and correspondingly the weights associated with these two, let's call them as w1 and w2. And now it will be quite obvious to the users what we are trying to really do over here. So being engineers, our job is to figure out the correct values of w1, w2 and theta, so that for all the possible 4 combinations, it's a 2 input system, so there are 2 to the power 2 4 possible combinations, and these are those 4 combinations 1, 2, 3 and 4. So I want to figure out the values of w1, w2 and theta, so that for all the 4 possible combinations of x1 and x2, my system should be able to produce the desired output y. How do we solve this particular problem? Well, the most common approach which is typically taken up majority of the times is what is known to us as heuristics, and we typically try this trial and error method out majority of the times. So I will say, okay, I want to solve this particular problem, so let me begin with some values, randomly selected values of w1, w2 and theta, and let me see whether it works. If it doesn't work, I will understand why exactly that combination is not working out, and then by virtue of making certain appropriate changes, hopefully I should be able to solve this particular problem. I should be able to figure the things out and be able to come up with the correct answer. So let us say we start this problem by selecting some random solution. Let us say we choose, let w1 be equal to 1, let w2 be equal to 1 and let theta be equal to 1. So we start off with these initial values, and I want to find out whether it really works or not. And to figure that out, what we are going to do is we are going to come up with empirical evidence. So I am talking about creating an empirical evidence, and what we mean by empirical evidence is we are going to actually excite our systems with the inputs and see whether the desired output is produced or not. So we are going to excite our system with x1 to be equal to 1 and x2 to be equal to 1. So I am talking about this very first kind of exemplar, and now I am going to slowly and gradually introduce the pattern recognition terminology to our viewers. So all these input combinations of different various inputs, these are typically called as exemplars, and since this is 2 input system, there are 4 possible exemplars for different values of x1 and x2. And for this very first exemplar where x1 and x2 both are 1, the desired output y is equal to 1. And for the values that we have chosen w1 1, w2 2 and theta to be equal to 1, let's try and figure out whether this works or not. And you will realize that it's a simple linear system, so we are going to add the things. For the time being, we are not going to consider the bias, and probably in next few examples we'll ignore bias and then we'll introduce the bias term, which is going to make our systems even more interesting. But let's start with simpler things. So when my system is excited with x1 is equal to 1 and x2 is equal to 1, what is going to be the value of my y of n? So y of n is equal to what? That is the question. And you will realize that it will be x1 into w1, that is 1 into 1, plus x2 into w2, again 1 into 1, and since this is my adder, it is going to simply add everything up. And so in this particular case, y of n is going to be equal to 1 plus 1, and that is 2, and that goes in as an input to my activation function, and the theta, the threshold value selected for activation function, is equal to 1. And if you look at our activation function, I can probably mathematically write down the formula so that it will be absolutely clear in our minds as to how my activation function is going to work. And I would probably say that y is going to be equal to 1 when y of n is greater than or equal to my theta value, and it will be equal to 0 when y of n, when y of n is less than theta. So this is how we can mathematically encode our activation function. And now, keeping this mathematical form in our mind, you will realize that y of n is definitely greater than my theta value, and as a result of that, the output produced is going to be equal to 1. And so I would say that fantastic, the first condition is met. I was able to confirm when x1 is 1 and x2 is 1, the output produced by my system is equal to 1. But that is not enough. We'll have to make sure that these weights and the theta value, they work for all the 4 combinations. So let's work it out for second exemplar, and this second exemplar I am talking about is when x1 is equal to 1 and x2 is equal to 0. So now x1 is going to be equal to 1 and x2 is going to be equal to 0. I am talking about exemplar number 2. So naturally, what will be the value of y of n? It will be 1 into 1 plus 0 into 1. So y in produced is going to be equal to 1. And what will be the final output y? We already know this particular formula for activation function, and so the output produced y, since y in is exactly equal to theta and I have this equal to term in the mathematical formula, so the output produced is going to be equal to 1, and that is not something that we want. The expected output is 0, and so we will realize that for the second exemplar it doesn't simply work. You can also excite the system for the third exemplar and you will realize this fact that it doesn't really work for the third exemplar as well, and for the last exemplar it once again works, but we want it to work for all the 4 exemplars, and that's why the selected values of weights and threshold, it's not serving the purpose, and so we'll have to make appropriate changes. Now viewers will also appreciate this fact that this is the very first example and we are doing it trial and error, and being engineers we are not interested in doing this trial and error. Instead of that, we want to build algorithms and we want a concrete set of rules that will tell me you follow these set of rules and you should be able to get the correct final answer. That's what we are interested in, and that's precisely I am driving this discussion towards. There is no fun doing the things trial and error, but let's see how human brain works. So when I am solving this particular problem, the viewers are also solving this with me, and please understand how your brain is responding back to interesting questions which are getting posed, and by virtue of that we should be able to take clues and be able to build our systems. So this is not working out, and then what should we do? We'll have to look at this second condition when x1 is equal to 1 and x2 is equal to 0, and what we really want to produce is 0 as the output, and so probably I can stretch my threshold value, and users can realize that instead of keeping this to be 1, if I convert it to 2, then I should be able to solve this particular problem. So instead of 1, if I change my theta value to go to 2, then it is going to solve my problem, and it's quite obvious. When both of them are 1, only then y of n will be equal to 2, and that is going to be equal to my threshold value, and only at that time the output produced is equal to plus 1. So what we realize by the end of this particular exercise, what we actually realize is the correct value of W1 could be 1, the correct value of W2 could be 1, and the correct value of theta could be 2, and this combination really works, and this combination will help us mimic the 2 input and kind of a gate. But again, there are very interesting questions which we can pose. Number 1, what is the guarantee that solution definitely exists? Can solution exist for any and every kind of a problem? We don't know the answer yet. What is the guarantee that the philosophy and the algorithm that I am trying to make use of for solving a particular problem, it will definitely converge to certain kind of a solution? What is the guarantee that the solution is unique, if at all it exists? And if the solution is not unique, and if there are thousands of different possible solutions, then who is going to tell me which is the most optimum of these different solutions? We are interested in pushing this discussion in that direction. Artificial neural networks, machine learning is about generalizing the concepts and generalizing the ideas. It is not just solving a particular problem. Instead, what we are more interested in is probably understanding the nature of the problem and then propose a solution that will fit with the nature of the solution that gets demanded out of the underlying nature of the problem. Now, what do we mean by the nature of the problem and the nature of the solution? It will be clear to our viewers in few moments as we go deeper in this particular session. I have a request that the viewers can try out a few other examples with the likes of OR functionality and not kind of functionality on their own, and they should be able to come up with the appropriate answers of the exact values of W1, W2 and theta. But like I mentioned, we are not interested in doing this trial and error. We want more concrete answers, and that's precisely where I would like to introduce the viewers to the most primitive kind of learning mechanism. So what we have seen so far is the hardware, the hard part of it, the actual neuron and how it is built and how I can build an embedded system out of it. And now what we are going to study is the soft part of it, the actual learning part of it, as to how I can make adjustments in the values of weights and biases to be able to come up with the correct solution to my problem that I am trying to solve. And that's where the major limitations of the McCulloch-Pitts model that we have seen is the weights are fixed, the weights cannot change, and we have to study a learning mechanism to be able to change the weights, and that's why McCulloch-Pitts model is considered as incapable of learning. And now we are going to convert it into a learning kind of a machine. And how do we do that? We'll do that by introducing a very interesting concept of an algorithm, the very first, the most primitive kind of learning algorithm, what is known to us as a Hebbian kind of a philosophy or a Hebbian kind of a network. And this particular scientist, Dr. Hebb, he was responsible for giving us this particular algorithm. And if you try and look at this particular algorithm, the algorithm is quite straightforward. Step number 0 talks about initializing of the weights and the biases. Step number 1, it essentially talks about making sure that the system has well connected inputs and well driven outputs. Step number 2 essentially talks about exciting the system with the stimulus, and then it also talks about ensuring that the target values are set as the output values. And then we have step number 3 and step number 4, which are even more interesting. So as far as step number 3 is concerned, it talks about how we can update our weights, and step number 4, it essentially talks about how we can update the bias values. So this is where the updation formula is given for the weights, and this is where the updation formula is given for the bias. So I can very well write down that delta Wi, the change in my weight, is essentially equal to x of I into y, and delta of B is essentially equal to y. So these are the places where exactly the changes are going to happen, and this is what makes this particular algorithm a learning kind of an algorithm. The viewers will also realize this fact that the formula that we have been using for learning is what is known to us as a dot product formula. So this is a dot product or the inner product between input x of y and output, that is y. Why this algorithm is called as learning algorithm, and these two steps 3 and 4 are so important, and they will make our system enable the paddles so that the underlying patterns can be learned. So why this algorithm is a learning algorithm and a learning mechanism, we will be able to understand this by virtue of solving a very simple problem once again. So we can repeat the same problem that we saw earlier, that is the case of 2 input AND gate. However, we are going to make a slight improvement in our model, and that improvement will be like this. So what we really intend to do is bring out a slight change in this particular model, and what we really wish to do is I am going to introduce the bias term, and I am also going to explain why bias is really important and how critical bias is in terms of making the adjustments with reference to the final decision that my system is supposed to take. So let us take the case of 2 input AND gate once again. However, we are now going to introduce a concept of 2 input bipolar AND gate. So now the system that I would like to make use of is going to be bipolar instead of binary. So all my inputs and targets will be bipolar instead of just being binary, and that's because you have realized in Hebbian kind of a philosophy we are going to make use of a dot product between input and output. Now when a 0 is multiplied with anything, it results into a 0, so that destroys the learning ability of your system. So instead of that, we will be making use of minus 1s in place of a 0, and a typical truth table for a 2 input system, x1 and x2 being those 2 inputs and y being the output, will look like this. When both of them are high, then they are going to produce an output that will be high. Both of them high, x1 and x2, only then it will produce a high output. For this exemplar 1 and minus 1, the output produced will be minus 1. For minus 1, 1, the output produced will be minus 1, and both low, definitely the output will be low. It goes without saying. So this is the system that we want to mimic now, and we are going to make use of the Hebbian philosophy that we have already seen. It's a very simple philosophy but very effective, and what makes it effective, that is something that we are interested in finding out. So let's begin our journey, and in this journey what we are going to do is we are going to calculate the values of W1, W2 and bias B, and initially these values will be set to 0. In this journey we are also going to study the changes in these values, that is delta W1, delta W2 and delta of B. So this is again something that we are interested in calculating, and I have already mentioned that the actual learning happens in these deltas. By the formula we know that delta W1 for example will be x1 dot y. So I am talking about a dot product between x1 first input and output y. So let's first of all run through the algorithm. Let's first of all solve this for all the 4 exemplars. Let's find out what this algorithm essentially gives us, and then slowly and gradually let's also explore that why this particular algorithm is called as a learning kind of an algorithm. So Let's excite our system using the first exemplar. By the way, when we are done with all the 4 exemplars, we say that one epoch is done. So a combination of all the exemplars is what is known to us as an epoch, EPOCH. But for the time being, let's excite our system with the first exemplar, and that is 1 and 1. And delta W1 now will be x1 into y, and x1 is 1, y is 1, so delta W1 will also be equal to 1. Delta W2 will be x2 into y, so it will also be equal to 1, and delta B is exactly equal to y. So if you remember the algorithm, we have already talked about this fact that delta B is exactly equal to y, and this change we are going to add into the bias value. So delta B is exactly equal to y, and whatever y values I have, I am going to repeat them in delta B. The next step is we are going to add these values in the old values to be able to produce the new values of weights and biases, and when I do that, I get all the new values of weights and biases. So adding ones into all those zeros will make my W1, W2 and B to be equal to 1 by the end of this first exemplar, and then I can say we are done with exemplar number 1. Now let's excite our system for exemplar number 2, that is x1 is 1 and x2 is minus 1. So delta 1 in this particular case will be minus 1, delta 2 will be equal to 1, delta 2 will be equal to 1 because x2 is minus 1 and y is also minus 1, and delta B will be equal to minus 1, exactly same as y. And once again we will add these into the old values to be able to generate the new values. So when I add these values, it will give me the new values, and that is going to be equal to 0 and then 2 and then a 0 once again, and then I can say we are done with exemplar number 2. Now let's excite our system for exemplar number 3, that is x1 is minus 1 and x2 is plus 1, and then what do we get? Delta 1 in this particular case will be equal to 1, delta 2 will be equal to minus 1, and delta of B will be exactly equal to minus 1, same as output y. Again we will add that into the old values, and that will give me 1 and 1 and minus 1, and we are done with exemplar number 3. And now let us deal with the last exemplar where x1 and x2 both are minus 1. So delta W1 will be equal to 1, delta W2 will be equal to 1, and delta B will be equal to minus 1. We will add these values into the old values of weights and biases, and that will give me 2, 2 and minus 2, and essentially Dr. Hebb tells me that these are your correct values. W1 will be equal to 2, W2 will be equal to 2, and bias will be equal to minus 2. Now the question is whether this really works or not, and there are two ways of answering this question. One is the empirical evidence, and the second one is what is known to us as the analytical evidence. Now empirical evidence is okay because that is going to tell us whether it works or not, but engineers are always more interested in analytics, and by virtue of doing the analytical part of the solution, we will be able to understand the nature of the problem and the nature of the solution. We will be able to realize if at all it works, why exactly it works, and whether it is truly a learning algorithm or not. We will bring both these points out, and then probably we will conclude this first session. But let us figure out whether these values they actually work, and if at all they work, why exactly do they work. And to figure this out, we are going to do this again systematically. So first things first, I am going to bring out the hardcore empirical part of the system, and in the empirical part what we really wish to bring out is this fact that if I want to build a system like this, wherein this is my adder and this is my thresholded activation function, and this is my input x, this is my input, another input x2, this is my output y, this is my intermediate output y of n, and then I have this term what is known to us as bias. Now let us once again introduce and bring out this very interesting concept of bias. Please understand that bias has a very special meaning, but at the time of studying multilayer perceptron we are going to bring that concept up once again, but at this point in time the viewers can understand that without bias, if I do not have bias in my system, then the mathematical equation of my system will look like this: x1 into w1 plus x2 into w2 is equal to theta, and then I have to keep changing the theta value, plus 1, plus 2, minus 1, minus 2, depending upon the nature of the problem, and it becomes inconvenient because ultimately we want to create an embedded solution of this system. So typical demand from the embedded plethora is to be able to come up with a block. So I want to create a block of my activation function, in fact different blocks with different activation functions, and once I say that this particular block is for a threshold kind of an activation function and the threshold value is set to 0, let us say we have set the threshold value go to 0, then nothing is going to change. All that I have to ensure is this bias term is equal to minus of theta value that I want to propose originally, and that will ensure that it is getting equated with that specific actual threshold value that we intend to push. So it is like this: without bias all the sum is getting equated with the actual threshold value. With bias we actually convert that sum so that we will be able to equate that with a threshold of a 0. So this is fixing up my threshold value to 0. We are going to solve the problem and then it will be very clear to our viewers as to what exactly are we talking about, and we are going to keep this bias term because it is quite handy. And what has been told to us by Dr. Hebb is W1 is equal to 2, W2 is equal to 2, and this bias is equal to minus 2, and whether this works or not, and we can verify this for all different cases, but I am going to probably just bring out the very first case wherein x1 is equal to 1 and x2 is also equal to 1, and what is the expected output? Since this is AND gate, when both inputs are high the output should be high. So you will realize x1 into w1 will give me 2, x2 into w2 will give me another 2, that will get added up, and the bias is minus 2, so 2 plus 2 minus 2, and so what yn will get produced will be equal to 2. Now this is definitely greater than my threshold value of 0, and so output produced is going to be equal to plus 1, and so this works. Let us also very quickly verify another case when the expected output is minus 1, and I am talking about a case wherein probably x2 will be equal to 1 and x2 will be equal to minus 1. So when x1 is 1 and x2 is minus 1, then what will be the value of y in? So 1 into 2 and minus 1 into 2, they will destroy each other, and the bias will be exactly equal to y of n. So y of n in this particular case will be minus 2, and since minus 2 is less than my threshold value of 0, the output produced is going to be equal to minus of 1, and this is very interesting. So now the solution that was found out using the Hebbian kind of philosophy, it is working out, and the viewers can confirm this for the remaining two cases, and they will be able to confirm that it indeed works for all the possible 4 exemplars. For the entire epoch, the solution actually holds good. But the question that we really want to pose is why exactly this algorithm works, because this is after all a simple dot product between input and output. And that's where the more interesting part, which is more important for engineers, actually comes into picture. And we would like to bring that analytical part very crisply, and then probably we will conclude this first session. But as far as the analytical part is concerned, we will be talking about the nature of the problem and the nature of the solution. So, why these values work, it is very important for the engineers to be able to understand this part. And let us try and understand what is the underlying problem that we are actually trying to solve. And if we really concentrate on the nature of the underlying problem, then you will realize this fact that if this is my x2 and if this is my x1, and if I plot the expected outcomes in a graphical form, then you will realize that when both of them are plus 1, x1 is plus 1 and x2 is also plus 1, then the expected output is plus 1. So, that is the nature of my output that is expected. For all other conditions, the expected output is minus 1. And if you look at it carefully, now this becomes a classification problem. I am trying to classify, I am trying to separate out, I am trying to cluster all these minus 1s from the plus 1, and this is the nature of the problem. And can I solve this problem using the Hebbian philosophy? And we will answer this question by virtue of once again invoking the underlying maths. The underlying maths now says that x of 1 into w of 1 plus x of 2 into w of 2 plus bias is equal to my theta value. And now if I plug in these values, you will realize w1 is 2, so 2 times x1 plus 2 times x2 plus bias term is minus 2. So, minus 2 is equal to theta value is 0. So, that is the mathematical equation that we get, and I can cancel all these 2's, and then the equation I will be left with is x2 is equal to minus of x1 plus 1. So, that is the equation I will typically get out of this particular system. X2 is equal to minus of x1 plus 1. And now if you compare this against y is equal to mx plus c, then you will realize that y axis is x2 axis, x axis is x1 axis. So, x2 is equal to minus x1 plus 1 is an equation of a line that has a y intercept of plus 1 and a slope of minus 1. So, I am talking about a y intercept of plus 1 and a slope of minus 1. So, typically that line will look like this. So, this is this particular line that we are talking about, and you will realize the fact that this line actually does the job. So, on one side of this line we have plus 1s, and on another side of this line we have all these minus 1s, and so it essentially does the job for us. So, it is a typical classification problem, and the nature of the solution is what is known to us as linear regression, or it is also called as constraint optimization problem. But what we have seen through this particular example is the Hebbian philosophy is capable of giving us this particular solution, which is a linear regressed kind of a solution. It is a constraint optimization solution. It does the classification. However, what we have not yet confirmed is whether this works for all different problems. If at all it works, then what is the convergence criterion, why exactly it works? If it does not work, then why it does not work? If at all it is going to produce multiple different solutions, then what is the most optimum of all these solutions? So, these are few of the questions which are still open ended, and we are going to systematically, slowly and gradually bring everything out so that it will be conveniently understood by our viewers. But what we saw in today's class, let's very quickly take a recap or summary of what we did in this very first class. See, this is a course on machine learning, and there are going to be three parts of this course. The first part will be dealing with artificial neural networks, the second part will deal with fuzzy systems, and the third part will deal with genetic algorithms. We have started with the first part, that is artificial neural networks, and what we saw in this particular class was the most primitive model of artificial neurons that was proposed by McCulloch and Pitts, and then we saw the very first, the most primitive type of learning mechanism that was proposed by Dr. Hebb, and that's what is known to us as Hebbian principle or Hebbian philosophy or HebbNet. We are going to harp on this. We'll be building on top of this, and in the next class we are going to understand the limitations of the Hebbian principle and what we can actually bring on table to take care of these limitations is going to be the subject matter of next particular session. Thank you so very much for your time and attention for this particular session, and we will build on top of what we have seen in this class in the next session. Thank you so very much.